To Ready to Derive. Thus far in the calculus series, we have only been interested in finding the slope of a tangent line at a point on a function, aka the value of the function's derivative here, because this gives us the instantaneous rate of change at that point, which is so helpful in applications. So for example, if the function was one that related the population of a species over time, then the slope of the tangent line would tell us how fast the population is changing at that moment. If the function was one that related the position of a projectile with time, then the slope would tell us the velocity of the projectile at that moment. In this video, we will take this one step further and learn how to find the equation of the tangent line at a point and also that of the normal line. What is a normal line? It's the line perpendicular to the tangent line at the point in question. And why does it matter? Well, let's imagine a car driving up a hill, and let's think about forces and physics. So here's the car. So the force of the engine that pushes the car up the hill is a tangential force. The force that resists that motion is also tangential, and that's friction. And the force that supports the car, i.e. prevents it from falling through the road, is known as the normal force. This force is perpendicular to the road and thereby perpendicular to the tangent line. So we know that the slopes of the tangent and normal lines will be negative reciprocals. I bring this up because it's nice to keep real-world context in mind as you delve into calculus, so you always understand the application of the methods that we learn. But enough of a preamble, let's get started. So let's begin by loosely defining a tangent line. I say loosely because it's not a rigorous definition, but it's a good working definition. So a tangent line to a curve is that line which touches the curve at one point, known as the point of tangency, and no other point in the vicinity of that point of tangency. So here's an example. The orange line is the tangent line, and this point that it's touching down on, let's call that P, that would be the point of tangency. And as you can see, that tangent line does in fact cross the curve again, at this point Q, but that's not really what matters. What matters is in the vicinity of P, this area in the neighborhood of that point P, that orange line, the tangent line, only intersects the curve once. So to see why the tangent line is such a useful construction in calculus, let's just zoom in to the area around the point of tangency, like this, and now we're going to sort of zoom in a little further. And as we begin to zoom in, notice that the function, the green curve, seems to be flattening out. And it almost looks like it's hard to distinguish between the tangent line and the function at that point of tangency. So let's go take it one more step. And if you really zoom in, the function appears linear at that point. It almost looks like the tangent line and the function are superimposed. They're not quite, right? They only meet at one point. But the tangent line becomes a very good representation of the curve in the vicinity of the point of tangency. This process is called linearization, and we will learn about this in a later video. But you can see that by having the tangent line approximate the curve, we can actually really simplify some calculations that would otherwise be very hard, as we will see in the next slide. So let's take a look at the function that describes this cool curve. Here's the function. It's quite a handful. And so any calculations I did with this function, I did with the graphing calculator to facilitate. So let me now give you the equation of the tangent line. I'd like you to think a little bit about where the numbers came from. So it's in point slope form. So y minus y1 equals m times x minus x1. And that's our x1 value is 2, obviously. So take a moment to think about where do you think I got, or how did I get 0.2826, the y1 value? Well, we have the equation of the function, so we should know that if all you have to do is take the function, plug in x equals 2, and that will give us the desired y1. And then here's the slope, 0.8771. Where did I get that from? Well, obviously everything we've done in calculus this far has led to this point, which is that the slope of the tangent line is given by the derivative of the function evaluated at 2. in this case. So again, that's not so easy to take the derivative of that function by hand, but the graphing calculator helped with that. So, so why bother, if we have the function itself, why do we even bother coming up with the equation of the tangent line? So, well, let's consider a slightly harder calculation. So, and then imagine you're in the 17th century and you're trying to do calculations by hand. Admittedly, you may not be using this function, but nonetheless, even another function, if you wanted to find the value at a nearby point like 2.001, that would be kind of tedious. But I'm going to tell you from the graphing calculator that this comes out to 0.2835. Now imagine that you're in the 17th century and you come up with the equation of the tangent line, and you think to yourself, well, why not use the equation? So, I know if I can plug a value of x in here, I can find out y by just solving the equation. So that's exactly what I'm doing here. And notice at this point, from this point onwards, I'm not actually going to use a calculator because I can do these calculations. That will be 0.001. Even multiplying by 0.001, I know I can move the decimal place over 3 places. And then all I have to do is add 0.2826 to both sides, which I can also do by hand. And believe it or not, I get 0.2835 also to 4 decimal places. I get the identical answer. And after 4 decimal places, they start to deviate slightly. So let's look at this in a graph. So, and the reason they come out so close, as you see when we zoom in, is that, once again, the tangent line is almost indistinguishable from the curve. So if we look at x equals 2.001, and we follow that up to the tangent line, and we come up with 0.2835, well, at that point they're so close together, they're almost indistinguishable. And that's why the tangent line becomes such a good approximation to the function itself. So we'll learn more about this process called linear approximation, also linearization, in a later video. So let's pause here to come up with a general equation for the tangent line, which we hinted at in the slide before, and also the normal line. So let's first consider the tangent line. So we have our function here, let's call it f of x, and we're interested in the slope of the tangent line, or the equation of the tangent line at a point. Generally we use a, and we know that if that's the x-coordinate of that point, then this must be the y-coordinate, and we would get it by working out f of a. So along comes the tangent line, and we know that the slope of that tangent line is just given by the derivative of the function evaluated at a. So our equation is as such. So y minus f of a equals f prime a times x minus a. That's in point slope form. And now let's introduce the normal line. This will be perpendicular to the tangent line, so we know we have a right angle here. And we know that both of these lines must pass through the point of tangency, whose coordinates are a, comma, f of a. So basically the equation of the normal line looks identical to the equation of the tangent line, except for the slope. We're acknowledging here that the slope of the normal line will be the negative reciprocal of the slope of the tangent line. So these formulas just help you to decide, figure out how you figure out y1 and how you figure out m, the slope. They haven't done any of the work for you. They just give you a structure for deriving these lines moving forward. So let's do a practice problem now. So we're going to find the equations of the tangent and normal lines to this function at x equals 1. So let's start with the tangent line. It would look like this. So it's always a good idea to, if you have a graph, to envision the tangent line and think about its slope, what you're going to be looking for in the equation. It looks like the slope is negative and reasonably steep, so keep that in mind. Okay, in terms of setting up these problems, I always recommend to kind of create a structure. So I'm going to lay it out like this. So we're going to start by finding the function and the derivative, and then we're going to find the value of the function at x equals 1 and the value of the derivative at x equals 1. If you have all these four components, you know you're not missing any detail. So if we start, well, let's start with finding f of 1. If we just plug 1 into here, 1 cubed minus 2 times 1 squared plus 4, if you work that all out, you will get 7/3. And now the derivative, using the power rule, the derivative of 1/3 x cubed will be x squared, and the derivative of minus 2x squared will be minus 4x, and the derivative of 4 goes away. So if we plug in 1 into f prime, we get 1 squared minus 4 times 1, which will be -3. So with that, our tangent line equation, TL for tangent line, will be y minus 7/3 equals -3, parentheses, x minus 1. And sometimes you may be expected to put that in slope-intercept form, but I find point-slope form much more useful, especially when we deal with the normal line. And that looks about right. It looks like if we go over here, if we sort of focus in at x equals 1, we look at that point, it's reasonable that that does look like 7/3 or 2 1/3, and the slope of -3 seems reasonable. So now for the normal line, which is perpendicular. So the normal line, again, the reason point-slope form is so good is that these coordinates stay the same. So x1 and y1 stay the same, and the only thing that we have to do is to take the negative reciprocal of the slope from before, which is 1/3, and there we have the equation of the normal line. So for our second practice problem, we're going to take the function from before, this function here, and we're going to find the equations of any horizontal tangent lines to this. And you can see that the horizontal tangent lines, it seems like there is one maybe around x equals 0, and one there around maybe x equals 4, but we also have to find the equations of them. And the position of horizontal tangent lines, the location of those are often important in applied problems using calculus. When you want to find kind of the maximum or minimum value of a function, you need to know how to locate the position of horizontal tangent lines. So obviously, if we want horizontal tangent lines, we need the derivative there to be 0. So let's call up the derivative function, and we are asking where is the derivative equal to 0? And then we just factor and confirm that we have horizontal tangent lines at x equals 0 and x equals 4, as we kind of predicted. But we do need the equations of these horizontal tangent lines. So let's take at x equals 0. So to get the equation of that, we really just have to plug 0 into the original function. And if we plug 0 into that, we will get 4. So that's the location of one horizontal tangent line. So that's this one up here, y equals 4. And then if we repeat with x equals 4, we're going to plug in, so 1/3, 4 cubed, right? Remember, you have to plug into the original. Do not plug into the derivative. If you plug x equals 4 into the derivative function, you'll get 0, not surprisingly, because that's how we got 4 in the first place. So you have to plug it back into the original to find the actual y value on the function. If you do the math here, you'll get -6 2/3. So our other tangent line is at this position, and that's the equation of this line. Y equals -6 2/3. So let's end with one last practice problem. Find the equation of the tangent line to this function at x equals 0. So I'm going to set up my structure. So notice that I put f of x into power rule ready form. I turned it from a radical to a rational exponent. I'm going to want to find f of 0 to find the y coordinate of that point. I'm going to need to find the derivative function, and then once I found that, I can plug in 0. So let's work on the derivative a little bit down here. So by the power rule, I'm going to get 1/3 x to the -2/3 minus 1. And if you're going to have to plug into the derivative, it's a good idea to get it back into radical form. It's much easier to plug in when it's in that form. And so it looks like it's going to be 1 over 3 cube root of x squared minus 1. So we'll put that up here. So we're ready to substitute in momentarily. Let's start with f of 0 though. That's an easy one. F of 0 is going to be 0. So that means we're looking at the equation of the tangent line at the origin on this function. And now let's plug 0 into f prime. So we get 1 over 3 cube root of 0 squared minus 1, which is 1 over 0 squared 0 cube root of 0. Oh, 1 over 0 minus 1. That is a problem. 1 over 0 is undefined, and the minus 1 makes no difference. So what is going on here? That the derivative is undefined at the origin. Let's take a look at the curve. And here we see that, oh, well, at x equals 0, at the origin, it does look like if we try to draw the tangent line, that it would be vertical, so its slope is undefined. Now notice that that tangent line is very unusual. It actually cuts through the curve. It doesn't rest. Most tangent lines, right, we're accustomed to them resting on the curve at the point of tangency. This one actually intersects the curve, but it's still tangent at that point. So it does have an equation. It's the equation of a vertical line. So the equation of this line would be x equals 0. Its slope is undefined, which means you can't go putting it into point slope form. So just be prepared to, find that a value substituted in the derivative is undefined, and watch out for the presence of vertical tangent lines. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.